I remember as a child that I was fascinated by maps. And in a way now we have constructed our map of the brain vasculature, allowing us to travel into the smallest branches of the blood vessels and explore.
A detailed map of the vascular system in our brain on both molecular and cellular levels. This is just one of Christer Betsholtz's contributions to science and to his own field of vascular biology in particular.
Our questions deal with how the small blood vessels in our bodies work, how they are composed, what cell types make them, and how these different cell types function and how they function together with each other.
Our network of blood vessels plays a major part in our body's daily life. Every second, it supplies oxygen and nutrients to our organs and disposes of their waste or carries immune cells around the body. These vessels are made up of various cells, and notably the pericytes in their outer layer. The purpose and the functioning of these cells is what caught the attention of Christer Betsholtz. Like all the cells in our blood capillaries, pericytes can apparently adapt themselves to the organ they serve. This is also true in the brain and in the blood-brain barrier in particular, which is where Christer Betsholtz has focused his research.
The blood-brain barrier is a way for nature to protect the brain from everything toxic that is flowing in the blood. But at the same time, all the good things in the blood that the brain needs, like sugar and amino acid and oxygen, has to be transported across the blood-brain barrier. Some of the very special features of the blood-brain barrier seem to be regulated by the pericytes in the brain. So in this sense, the brain pericytes have a specific role.
Christer Betsholtz and his team sought to discover and better understand the fundamental role of pericytes in the formation and adaptation of the blood vessels connected to the organs they supply. The blood-brain barrier is truly fascinating. On the one hand, it protects our brain, but at the same time, it complicates medical treatment of diseases affecting it. It's an ideal field for research.
It's not easy to work on the blood-brain barrier because it's such a tight structure and such a complicated structure also. And also because the technology that we use to really analyze it is very novel and very much under development. So it's a really spearheading type of research. So it's just very fascinating to work because the field changes every single day. And it's never boring.
On the screen we see the retinal vasculature of a mouse, which is stained for endothelial cells in red and for mutant cells that we are studying in green. The new technologies which we are using here, they give us the possibility to study things in more detail than it was been able before. And we can learn more about the cell biology of disease.
We were looking at the retina and the vasculature and also how the pericyte, how they are surrounding the vasculature. And as we are looking at those things for the first time, we need a lot of discussion between us to see if we are interpreting what we see it the same way, or we have different hypotheses, or we have different thoughts about what we see.
From the tip,
yeah,
they are normal.
Yeah, and
here they become like bubbles.
Yeah, look at this.
Wow, that's amazing. One microglial cell has.
I saw in front of the microscope, for the first time for me, something that I found extremely exciting, somewhat paradoxical, and I tried to convey that excitement and explain to Konstantin and Barbara why I thought this was so interesting, such an important finding or such an important observation to pursue.
He has the eye for discoveries in the molecular, really tiny details, and he can move that into a general concept or make a new concept if it wasn't there before. And so this creativity combined with his ability to install new technology or invent new technology when it's not there really makes him a very special scientist.
Professor of Vascular and Tumour Biology at the University of Uppsala, located north of Stockholm, Christer Betsholtz is also director of the AstraZeneca Karolinska Instituted Integrated Cardio-Metabolic Center. Different but eminently complementary workplaces where fundamental and applied research come together. A blending and multiplying of universes pushing back the horizons of knowledge, and in keeping with Christer Betsholtz's ideal that science should be at the service of all.
I'm often asked by my younger colleagues, should we talk about our unpublished data? Isn't there a risk that we would get scooped? Somebody would steal our ideas? And my answer is that in most cases not. And by sharing information already before publication, in my career I've only seen benefits. I think it's also a way to get others' opinions on not only what are the important questions, but also how to answer them.
It's more fun, it's more exciting. So together you can get the feeling that you're really learning something. Your work is worthwhile. There are even more groups here. We're a couple of groups, and we're attracting young researchers from all over the world to come here. So we're growing and doing more and more together, but also in different ways, and the quality gets better.
The Swedish model, where hierarchy is practically absent, encourages a unique work environment and facilitates interaction. The country is known for the Nobel Prizes awarded every year, and this contributes to an awareness of science in general among the Swedish population. It's in Sweden, his home country, that Christer Betsholtz has undertaken most of his research and where he plans to continue his work.
Year after year he's made important contributions to that, both how the vascular system is organized and how it branches, and also the blood-brain barrier work, and now recently also looking into the different cell types that exist in the vascular system. So that's a long string of important contributions.
So right now we are really expanding the findings that we have in the brain and comparing them to other organs that have very different functions, and we can see if the vasculature has similar functions in these organs or if it's just completely different. So it will also change the very definition of vasculature.
Understanding precisely how the vascular system works in our brain and elsewhere in our body, explaining how neurovascular diseases develop and how to treat them, such are some of the objectives Christer Betsholtz and his teams have set themselves. These are wide-ranging, but nonetheless achievable goals.
To mentor young scientists and help them in their career, I'm coming back to these early choices that I made, where I followed my curiosity and had this wish to explore the unknown and go my own way. But then there is the career to think of as well, and it's harder, it takes longer, and it's harder to publish the research which is coming from the unknown field, an unexplored field.